Good evening, ma'am. My name is Sai from Computer Science and Engineering. My subject database management system. Today my topic BioData Grid. Introduction to BioData Grid. BioData Grid is a distributed data management system designed to handle large-scale biological data datasets such as genomic, proteomic, and clinical records. It enables researchers to store, query, and analyze massive volumes of biological data across multiple instructions and geographic locations. The system integrates data from heterogeneous sources like DNA sequencers, electronic health records, and public bioinformatics database. BioData Grid supports collaborate research by providing secure high performance access to shared biological data resources. Motivation challenges is biological data management. Biological data is growing exponentially due to advances in sequencing technologies and high throughput experiments. Data is often siloed across labs, hospitals, and research centers, making integration and sharing difficult. Researchers face challenges in accessing, querying, and analyzing distributed databases efficiently and securely. Traditional databases struggle with the volume, variety, and velocity of modern biological data stream. Core architecture of BioData Grid. BioData Grid was a large architecture, data large, metadata layer, query processing layer, and application interface. The data layer stores raw biological data across distributed nodes using replication and protecting prototyping strategies. The metadata layer maintains semantic distributions of datasets, including provenance, format, and access permissions. Query processing is declinized with queries decomposed and executed across multiple data nodes in parallel. Data modeling in BioData Grid. BioData Grid supports semi-structured and unstructured data module to accommodate diverse biological data types. It uses ontologies like Jenny ontology on Snemode CT to provide semantic consistency across datasets. Data is modeled as entities with attributes and a relationship defined using RDF or XML schemes. Scheme evaluation is supported to allow new data types and annotations without disturbing existing queries. Metadata and semantic integration. Metadata is biodata grid includes technology, details and domain specific and annotations, Jenny function, disease association. Semantic integration uses shared vocabularies and ontologies to glean data from different sources under a common meaning. The system employs a metadata catalog that enables discovery of relevant datasets based on biological content. Preventions metadata tracks data origin, transformation, and usage history to support reproductively. Query processing and optimization. BioDataGrid supports declarative queries using extensions of SQL or domain-specific languages like BioQL. Queries are optimized by considering data location, network latency, and computation load across needs. The optimizer selects execution plans that minimize data transfer and maximize parallelism. Distributed storage and data placement. Data is partitioned horizontally by biological entity, by chromosome or organisms, or by research project. Replication is used to improve availability and fault tolerance, especially for high demand datasets. Storage nodes are organized in a pair to pair or hierarchically topologically to balance load and scalability. Data placement policies consider axis patterns, geographic proximity, and institutional agreements. Security and access control. Biodata grid enforces role-based access control to restrict data access based on user roles and institutionally affiliations. Sensitive data such as patient genomes are protected using encryption and anonymization, anonymization techniques. Idiot logs tracks data access and modifications to ensure compliance with ethical and legal standards. Federated identity management allows user organizations to authenticate securely. Inter op, interoperability with external systems. Biodata grid contains to public responses like NCBI, EPI, and UNI Proto using standardized APIs and data formats. It supports data exchange in formats such as F- FASTA, VCF, and DICOM for genomic and imaging data. Middleware components translate queries and data between biodata grid and external systems. Scalable and performance consideration. Biodata grid scales horizontally by adding more storage and compute nodes as data volume grows. Load balancing distributes queries and data operations evenly across the network to prevent bottlenecks. Asynchronization processing and batch operations are used for long-running analysis like genome width association studies. Performance monitoring tools track query latency, throughput, and resource utilization in real time. Use case: genomic data sharing in cancer research. A institutional cancer conception used biodata grid to share tumor genome sequences and clinical outcomes. Research submit standardized metadata using the cancer genomic atlas. Scheme for considered consistency. Queries identify muti- mutation common across patient subgroups to discovery potential therapeutic targets. Challenges and limitations. Ensuring data consistency across distributed nodes required complex synchronization protocols. Heterogeneous heterogeneous data formats and evaluating ontologies complicate semiotic integration efforts. Network bandwidth can become a bottleneck when transforming large datasets for analysis. Regulator compliance adds complexity to data sharing across borders. Future directions and innovations. Integration with machine learning pipelines for automated pattern discovery in biological data. Adoption of blockchain for secure and transparent data prevention and access logging. Support for real-time streaming data for wearable biosensor and lab instruments. Development of natural language interfaces to allow biologic to query data using plain English. Thank you, madam.